Namaskar, my dear friends. Welcome to the lecture series of machine design. In our previous lectures, you have learned about the design of spur gear, design of helical gear, and design of bevel gear. And also, we were solved some examples of spur gear, helical gear, and bevel gear. Now, today, in this lecture, we are going to learn about the design of worm gear. Now, let us start with the content of this lecture. Introduction, terms used in worm gear, efficiency of worm gearing, thermal rating of worm gear, forces acting on worm gear, and design of worm gearing. Now, let us start with the introduction. Now, here you can see the two gears are there, and both the gears are at right angle with each other. Okay, so the worm gears are widely used for transmitting power at high velocity ratio between non-intersecting shafts that are generally but not necessary at right angle. Okay, and it can give velocity ratio as high as 300 gem1. It means if the speed of the driver is 300 revolution per minute, then it can reduce the speed of the driven up to the 1 revolution per minute or more in single step, okay, in minimum of space. Okay, but the drawback of this gearing is that it has the lower efficiency, and the worm gearing is mostly used as a speed reducer, which consists of worm and worm wheel gear. Okay, the worm, generally you can see this element. This element is known as a worm, and which is generally a driving member. Okay, and is usually of a cylindrical form, having thread of the same shape as that of an involute rack. Okay, so here you can see in this member there are threads, and is the same as the involute rack. Okay, and the threads of the worm, it may be left-handed or right-handed. Okay, and it may be a single or multiple threads. And the worm wheel, okay, the matting gear, here you can see this matting gear, this is known as the worm wheel or worm gear. Okay, and which is generally a driven member. Okay, it's similar to the helical gear, okay, which with a face curve to conform to the shape of the worm. And this worm is generally made of steel, and the worm gear is made of bronze or cast iron for the light service. Now, the types of worms. So generally worms are of two types. One is the cylindrical or straight worm. Here you can see this figure A is so the cylindrical or straight worm, in which one here this is the single threaded and this is the double threaded. And another one is the cone or double enveloping worm. Now, this cylindrical or straight worm, okay, is most commonly used, and the shape of this thread is involute, helicoid of pressure angle 14.5 degree. Okay, here the pressure angle phi is 14.5 degree for single and double threaded worm. Okay, and 20 degree, this value of the pressure angle is 20 degree for triple and quadruple threaded worm. These worm threads are cut by straight-sided milling cutter, having its diameter not less than the outside diameter of worm or greater than, okay, or greater than 1.25 times the outside diameter of worm. Then second one is cone or the double enveloping worm. Okay, so is used to some extent, and but it requires extremely accurate alignment. Then next one is the types of worm gear. So the worm gears are of three types: straight face worm gears, hop straight face, and concave face. So in the straight face worm gear is like a helical gear, in which the straight teeth are cut with a foam cutter. It has only point contact in this. It has only point contact with the worm thread. So therefore, it is used for light service duty. Okay. Then in this figure B, it's a hob straight face. Is also used for the light service, but its teeth are cut with hob. Okay, so after with the outer surface is done. And third one, or the figure C, it shows the concave face is accepted standard form and is used for all heavy service and general industrial uses. So the teeth of this gear are cut with a hob of the same pitch diameter as the matting worm to increase the contact area. So generally there are three types of the worm gears. Okay, worm gear is used mostly where the power source operates at a high speed and output is at a low speed with high torque. So it is also used in some cars and trucks. Now, next step is the terminology or the terms used in the worm gearing. Okay. Now here in this figure, you can see the two matting gears, worm and worm wheel. Okay. The two views are there, and this is it shows the pitch cylinder and the different angles are there. Okay. Now let us, first one is the axial pitch. So you can see this PA, it shows the axial pitch. Now what is the meaning of the axial pitch? So a distance, okay, it is the distance measured axially, or we can say the parallel to the axis of the worm. Okay, so the distance measured parallel to the axis of this worm, from a point of one thread, okay, point of one thread to the corresponding point of the adjacent thread, okay, on the worm. So here you can see this PA. PA is the axial distance from one point of this thread to the corresponding point of the adjacent thread. It is known as the PA or the axial pitch. The axial pitch of the worm is equal to the circular pitch PC of the matting worm gear. Okay, so PA is equal to the PC of the matting worm gear when the shafts are at right angle. Here you can see in this case both the shafts are at right angle. So here in this case PA is equal to PC, circular pitch of worm gear. Okay, so axial pitch. Then next one is the lead. So it is the linear distance through which a point on a thread moves ahead in one revolution of the worm. So for the single start thread, lead is equal to the axial pitch, but for multiple start thread, lead is equal to the product of axial pitch and number of starts. So mathematically we can say lead L is equal to product of PA and N, where PA is the axial pitch and N is the number of start. Now here you can see this L is the lead. In short, we can say when this worm, it rotates the one revolution, at that time the axial distance traveled by this thread is known as the lead. So for the single start thread, the lead is equal to axial pitch, and for the multi-start thread, or we can say the double start thread, then lead is equal to 2 into axial pitch. For the triple start thread, the lead is equal to 3 into axial pitch. So in short, we can say the axial distance traveled by thread, that is known as the lead. Then lead angle. The lead angle is denoted by the lambda. Now here you can see in this pitch cylinder, this angle is a lambda. Now what is lead angle? It is the linear distance. So it is the angle between the tangent to the thread helix on the pitch cylinder and the plane normal to the axis of the worm. Okay, so you can see this is the helix, okay, and this is the normal plane. So this angle is called the lambda and it is called the lead angle. Now here if we develop the one thread, or we can say we unwound the one thread, then you can see it will a right angle triangle. If we develop the one thread, then the height of this triangle is equal to the lead, and this is the circumference of that thread. So it is equal to pi dw, and here this is the normal lead ln. So this angle will be a lambda, and it is known as the lead angle. Now from this triangle we can say tan lambda. Tan lambda is equal to this side divided by this side. So this side is L. Okay, so tan lambda is the lead of the worm upon pitch circumference of the worm. So is equal to L upon pi d is equal to L is equal to PA into N, and pi dw is the diameter of worm. Now we know that the in single star this PA is equal to PC. So PC into N, and PC is equal to pi into M. Okay, so pi Mn upon pi dw. Now from this we can say Mn upon dw, where M is the module and dw is the pitch circle diameter of the worm. Okay, so lead angle you can find from this equation. Then next one is the tooth pressure angle. So it is measured in a plane containing the axis of the worm and is equal to 1/2 the thread profile angle. Okay, so tooth pressure angle, you can say here in this case, tooth pressure angle phi. Okay, so the recommended values for the lead angle and pressure angle. Okay, so lead angle lambda in degrees and pressure angle phi in degrees here. If the value of the lead angle is from 0 to 16, then the value of pressure angle is 14.5 degree. And if the lead angle is 16 to 25 degree, then pressure angle is 20 degree. If the value is 25 to 35, then it is 25 degree, and lead angle is 35 to 45 degree, then pressure angle is 30 degree. Now normal pitch ln, PN. So it is distance measured along the normal to the threads between two corresponding points on two adjacent thread of the worm. So mathematically this normal pitch Pn is equal to Pa into cos lambda. Okay. Now next one is a helix angle. So it is the angle between the tangent to the thread helix on the pitch cylinder and the axis of the worm, and it is denoted by alpha W. So the worm helix angle is the complements of worm lead angle. So therefore we can say alpha W plus lambda is equal to 90 degree. Okay, so here you can see this angle. This angle is alpha W plus this lambda is equal to 90. Okay, so this angle is a alpha W. Okay. Then here you can see this dW is the pitch circle diameter of worm. DOW is the outer diameter. Okay. This H is the height of this thread. Then velocity ratio. So it is the ratio of the speed of worm NW in RPM to the speed of worm gear NG in RPM, revolution per minute. So velocity ratio VR is equal to NW upon NG. NW is equal to pi into DG, and NG is equal to L lead. So DG is equal to M into TG. So pi M TG by L. So velocity ratio VR is equal to, again we can say pi M is equal to PC, circular pitch. So PC into TG by L, and PC is equal to PA, and L is equal to PA into N. So PA cancel. So therefore, velocity ratio is equal to TG by N. Okay, where N is number of starts of worm and TG is number of teeth on gear. So velocity ratio VR is equal to TG by N. Now, number of starts to be used on the worm for the different velocity ratios. So velocity ratios 36 and above. Then number of starts for the thread on the worm is single started. From 12 to 36 VR, it is double. From 8 to 12, then triple start. Okay, value of N is equal to 3. If 6 to 12, then it is quadruple, N is equal to 4. And if a velocity ratio is 4 to 10, then it is sextuple, that means N is equal to 6. Now, different proportions for worm gears, okay, the different values, standard values. Okay, so here normal pressure angle when the single and double threaded worm and triple and quadruple threaded worm. So normal pressure angle is 14.5 degree for single and double threaded worm, and for the 20 degree for triple and quadruple threaded worm. Pitch circle diameter for worm integral with the shaft is given by, that is the dW is equal to 2.35 PC plus 10 mm, and here in this case it is 2.35 PC plus 10 mm. Pitch circle diameter for worms bored to fit over the shaft, it is 2.4 PC plus 28 mm, 2.4 PC plus 28 mm. Maximum bore for shaft PC plus 13.5 mm, here PC plus 13.5 mm. Hub diameter 1.66 PC plus 25 mm and 1.726 PC plus 25 mm. Face length LW is equal to PC into 4.5 plus 0.02 TW, and here in this case PC into 4.5 plus 0.02 TW. Depth of tooth H 0.686 PC, here 0.623 PC. Addendum 0.318 PC, 0.286 PC. And proportions for worm gears, okay, normal pressure angle phi is equal to 14.5 degree and here 20 degree. Outside diameter DOG, DG plus 1.0135 PC, DG plus 0.893003 PC. Throat diameter DT is equal to DG plus 0.636 PC, DG plus 0.572 PC. Face width 2.38 PC plus 6.5 mm, 2.15 PC plus 5 mm. Radius of gear face 0.882 PC plus 14 mm and 0.914 PC plus 14 mm. And radius of gear rim 2.2 PC plus 14 mm and 2.1 PC plus 14 mm. Now let us efficiency of worm gearing. So the efficiency of worm gearing, it may be defined as the ratio of work done by the worm gear to the work done by the worm. Okay. So in short, mathematically, the efficiency of worm gearing is given by this equation. Eta is equal to 10 lambda cos phi minus mu 10 lambda upon cos phi 10 lambda plus mu. Okay. So efficiency is given by this equation where phi is the normal pressure angle, mu is the coefficient of friction, and lambda is the lead angle. So the maximum efficiency is maximum when this condition is satisfied. So 10 lambda is equal to root 1 plus mu square minus mu. Okay. So if this condition is satisfied, then efficiency of the worm gearing is maximum. Now, in order to find the approximate value of the efficiency, let us assume the square threads. Okay, so for that the relation efficiency eta is equal to 10 lambda 1 minus mu 10 lambda upon 10 lambda plus mu So is equal to, by simplifying this equation, you will get 1 minus mu 10 lambda upon 1 plus mu by 10 lambda. So is equal to 10 lambda upon 10 lambda plus phi 1. Okay. Substituting in equation 1, that is phi is equal to 0 for square thread. Okay. For square thread, the pressure angle is equal to 0. And phi 1 is the angle of friction. So such that this tan phi 1 is equal to mu. So the efficiency by assuming the square thread, f eta is equal to 10 lambda upon 10 lambda plus phi 1. Now, if the efficiency of worm gearing is less than 50%, then the worm gearing is said to be a self-locking. That is, it cannot be driven by applying a torque on the wheel. Okay. So this property of self-locking is desirable in some applications such as hoisting machinery. Okay. So in hoisting machinery, the efficiency of that worm gearing is less than 50%. Okay. Thermal rating of worm gearing. In the worm gearing, the heat generated due to work lost in friction must be dissipated in order to avoid the overheating of drive and lubricating oil. So the quantity of heat generated, Qg, is given by, okay, so Qg is power lost in friction in watts, is equal to P into 1 minus eta, where P is the power transmitted in watts and eta is the efficiency of the worm gearing. Okay, so the heat generated, it must be dissipated through the lubricating oil to the gearbox housing and to the atmosphere. So the heat dissipating capacity depends upon the different factors. Okay, and that factors are, that is the area of the housing, then temperature difference between the housing surface and surrounding air, that is T2 minus T1, and conductivity of the material, and it is K. Okay, so therefore the heat dissipating capacity. Okay, so heat dissipating capacity QD is given by one equation, that is QD is equal to A T2 minus T1 into K. Okay, so the thermal rating, or we can say heat dissipating capacity, you can find by this equation. Then next one is the forces acting on the worm gear. Okay, so when the worm gearing is transmitting power, the forces acting on the worm are similar to those on a power screw. Okay. So this figure, it shows the force acting on worm here in this case, and it may be noted that the forces on the worm gear are equal in magnitude to that of worm, but opposite in direction. Okay, shown here. So in case this worm, this is the worm shaft. Okay, worm gear, it is rotating in this direction. So you can see this WR is the radial load and WA is the axial load. Okay, and here in this case you can say this is the WT is the tangential load and WR is the radial load. Okay, so the tangential force on the worm is given by equation WT is equal to 2 into torque on worm upon pitch circle diameter of the worm, dW. Okay. So is equal to axial force or thrust on the worm gear. Tangential force is equal to axial force or the thrust of the worm gear. Now axial force or the thrust on the worm gear, WA is equal to WT upon 10 lambda is equal to tangential force on the worm gear. So is given by 2 into torque on the worm gear upon pitch circle diameter of worm gear dg. Now radial or separating force on the worm. So WR is equal to WA 10 pi is equal to radial or separating force on the worm gear. So the radial or separating force, it tends to force the worm and worm gear out of mesh. So this force also bends worm in the vertical plane. Now, next is the design of worm gearing. So in designing a worm and worm gear, the quantities like the power transmitted, speed, velocity ratio, and center distance between the shafts are usually given. And the quantities such as that lead angle, lead, and number of threads on the worms are to be determined. Okay. So in order to determine this satisfactory combination of lead angle and lead and center distance, okay, we have to find. So the center distance x here in this case, okay. So the dg is the diameter of gear, pitch circle diameter of gear. dw is the pitch circle diameter of worm. Okay. ln is the normal lead. Lambda is the lead angle. L is the lead, right? So the center distance x from this geometry, you can say center distance between these two. So distance, this distance x is equal to dw plus dg by 2. Okay, center distance is given by this equation. Now this center distance, it may be expressed in terms of axial lead L and lead angle lambda and the velocity ratio. So x is equal to L by 2 pi cot lambda plus VR. Okay, and in terms of normal lead, ln is equal to L cos lambda. So therefore the above equation, it may be written as x is equal to ln upon 2 pi into bracket 1 upon sin lambda plus VR upon cos lambda. So from that we can say x by ln is equal to 1 upon 2 pi 1 upon sin lambda plus VR upon cos lambda. Okay, so this velocity ratio VR is usually given. Therefore, the equation, okay, so from this equation it contains the three variables. That variables are x, ln, and lambda. Okay, here this three variables are there. So the right hand side of the equation, it may be calculated for various value of velocity ratio, and the curves are plotted. Okay, so if we plot a curves, okay, so this curves of a lead angle lambda versus x by ln at the various velocity ratio. Okay, so the lowest point on the each of the curve, it gives the lead angle. Okay, so lowest point on each of the curve, it gives the lead angle which corresponding to the minimum value of x by ln. Okay, so lowest point, it gives the lead angle corresponding to velocity ratio. And this minimum value, it represents the minimum center distance. Okay, that minimum value, it represents the minimum center distance, and that can be used with a given lead or inversely the maximum lead, and that can be used with a given center distance. Okay, so by using the table and standard module, we can determine the combination of lead angle, lead, center distance, and diameter for the given design specifications. Okay, so thank you very much, friends. I hope you can understand very well. Okay, and in our next lecture, we will solve the different examples of the worm gear to clarify this design procedure. Okay, so thank you very much.